Okay, we're now going to review for Chapter 7. So in 7.1, we learn about computing the confidence interval for the true mean. So the true mean is represented by mu. To do this, we collect a sample size of n. We calculate the sample mean x bar to approximate this true mean, mu. We use our normal distribution. We're assuming that the population standard deviation is known, and we look up our corresponding z-value in table F. So let's work out an example. A biologist wishes to estimate the average weight of male jacarandis. It's a type of wildcat that lives approximately in South America. He collects a sample of 30 jacarandis and finds that the sample mean is 18.5 pounds. The population, so population standard deviation is a key word. Once you see the population standard deviation in a problem like this, that's going to tell you to use this particular formula. It's 3 pounds. Compute a 95, and here's the key wording again. I highlight the key wording. A confidence interval of a true mean tells you that we're going to use this formula of all male jacarandis. So what I like to do is just kind of label everything that we're going to be using. So the population standard deviation is sigma. Well, we know that that's 3. Sample mean x bar, that's 18.5. Sample size n is 30. Confidence level is 95%. Population mean is unknown. That's what we're estimating. To find z, I'm going to show you how to look up z in table F. So our confidence level, let's make this a little larger. Let me go a little larger here. Our confidence level is 95%. So when we're looking for the z values, we go all the way to the very bottom of the 95% column. And we'll see that this 1.96, that's the z-value. Okay. So now the next step is we insert that information into our formula, as we've done here, and we just use order of operations and calculate. So we see that the true mean weight of jacarandis is between 17.43 pounds to 19.57 pounds. The next formula in this section that we have to use is to compute the minimum sample size. That's going to be the z-value times the population standard deviation divided by E. E is the maximum allowed error. Quantity squared. And we always round n upwards to the nearest whole number. Here's our example. Assume that a biologist wishes to estimate the average number of rosettes. Those are the spots on a jaguar. What is the minimum number of jaguars he must sample if he wishes to be within 4 spots? The standard deviation is 12 spots, and the confidence level is 95%. So let me just type in population standard deviation. Okay. That lets us know we're going to be using sigma. So once again, as we learned over here, 95% produces a z-value of 1.96. Sigma is 12. E is 4. We plug this into our formulas, take the square, we get 34.5744. But remember, you round up to the next highest whole number, which is 35. So the biologist would have to sample 35 jaguars. Now we go into 7.2. This is where we have to compute the confidence interval for mu when sigma is not known. So most likely sigma will not be provided. In that case, we have to use the sample standard deviation in place of sigma. And we do not use the z distribution or the normal distribution. We use the t distribution. So let's look at an example. A biologist wishes to estimate the average lifespan of a mountain lion. She samples 12 mountain lions and finds that the average lifespan is 10 years with a sample standard deviation of 2.4 years. So when you see sample standard deviation, that's letting us know we're working with the t-values. What is, once again, other keywords. What is the confidence interval using a confidence of 90%? That's going to tell us to use this particular formula, these two groupings of words. All right, so mu, once again, we're estimating mu. That's our true mean. X bar is 10, right, because that's the average lifespan for the sample of 12 mountain lions. Sigma is not given, so that tells us we're using t-values. S, the sample standard deviation, is 2.4. N is 12 because we sampled 12 mountain lions. So to find our t-value, we have to compute a concept called degrees of freedom. Okay, so that's a concept beyond the scope of our class. All we need to do is compute n minus 1. So 12 minus 1, 11. And then we go to table F. And remember, the confidence level was 90%. We go down to level 11 to get 1.796, which is what I have listed here. And then we take this information, plug it into the formula, and calculate. The true mean lifespan of a mountain lion is somewhere between 8.76 to 11.24 years. And the final section of Chapter 7 is 7.3. That's where we find the confidence interval for a population proportion. And so this right here is our formula. Remember, this notation here is called p-hat. P-hat is the sample proportion. We also need to find q-hat. Q-hat is always 1 minus p-hat. And that is your sample size. So here's our example. Compute the confidence interval of the true proportion, so that's P, the true proportion of people who own a cat. A sample of 50 random people were selected and 18 of them own cats. Use a confidence level of 99%. So step 1 is to compute the sample proportion. That's going to be X out of N. So we have 18 people who own cats out of a sample of 50. So 18 out of 50 is 0.36. Always round to 3 decimal places. In this case, it just came out to an even 0.36. Then we compute q-hat. That's the sample proportion of people who do not own cats. So that's 1 minus 0.36, which is 0.64. Okay, then we're going to look up, so whenever you're dealing with a confidence interval for P, what we have to do is we always have to look up the z-value. We don't use the t-value here. So let's go to table F again. We're going to look at the last column for 99% and go all the way down to the very bottom. And that's going to tell us what our z-value is. It's 2.58. And so I insert 2.58 in the formula along with these other values. And you just have to be real careful how you type in this information. You may want to look at my video for computing the confidence interval for a proportion, and always round to 3 places. So P is between 0.185 to 0.535. And just leave it in the decimal form when you write your answer. Now the last part of 7.3 is we have to compute the minimum sample size when we're estimating a proportion. And so our formula is p hat times q hat times z sub alpha over 2 divided by e, quantity squared. E is your allowed margin of error. We always round n to the next whole number. So here's our example. A biologist wishes to determine the percentage of black panthers in the wild. The standard sample proportion is 5%. So this is what we're going to use. This is our p-hat, 5%. How large a sample is necessary, that tells us we're looking for n. To construct a confidence interval of the true proportion of black panthers in the wild. Use a confidence level of 95%. Also, the error is to be within 0.05. So p-hat is 5%. 1 minus 5% is 95%. So we're going to represent that as 0.05 and 0.95. Let's look up our 95% confidence level. So that's going to tell us to go all the way down, since we're looking for a z-value, 1.96. So this z-value becomes 1.96. E is our error, 0.05. Type this in the calculator. We should have 72.9904, which rounds up to 73. So the biologist would need a sample at minimum 73 black panthers to estimate the confidence interval. If there's any, hopefully there are that number of black panthers in the wild. And so that concludes a review of Chapter 7. Thank you.